In this video, we're going to discuss solving systems of linear equations using something called a matrix. So before we jump into the technique here, I want to make a couple notes before we get started. First of all, the technique that I'm about to show you only works with systems of linear equations. Anything more complicated than that, and you need more sophisticated tools than what I'm going to show you here. Second of all, organization in this technique is crucial. You got to be very careful about it. In particular, you got to keep your variables aligned in columns, as well as your equal signs aligned in a single column as well. So the basic way that the technique works here is we're going to take a system of equations, translate it to a matrix, solve that system using some computational techniques on the matrix, and then translate back into a solution of the original system. So let's jump into a quick example here, and that's the system that's displayed as follows. X minus 2y plus 3z equals 11 is the first equation. 4x plus 2y minus 3z equals 4 is the second equation. And 3x plus 3y minus z equals 4 is the third equation. Notice here that all my variables are kept aligned in columns. All my x's are in a column, all my y's are in a column, and all my z's are in a column. In a similar way, all my equalities are in a column as well, and it's very important that you do this. So what we're going to do now is copy the original equation here, and we're going to start removing redundancies. The first thing that I'm going to remove, the first thing that I'm going to note here is that we have hidden coefficients on the z in the third equation and the x in the first equation. So I filled them in red here, and that's that red one in the first equation and the red one in the third equation on the z. Now we're going to start removing redundancy. First thing that I'm going to do is just erase the variables. Because of the way that we have our columns organized, we know where those variables are going to go, and this is exactly why it's important that you keep the columns lined up in terms of variables and equalities. Next up, I'm going to get rid of the plus signs on all of my positive coefficients. So here, I've erased the plus signs. We have to keep the minus signs to reflect the fact that the coefficients in the original equation were negative. Next up, I'm going to get rid of my equal signs here, and I'm going to replace where those equals used to be with a vertical bar here. Next up, I'm going to surround this entire block of numbers with some big brackets. And the result, what we get here, is called an augmented matrix. A lot of times you'll hear people just call this a matrix, but what the augmented refers to is that vertical line that we use to keep track of where the equal signs used to be. You'll notice that what we have here is just the coefficients that we had on the original system of equations. And the vertical bar represents the space where the equals used to be. So this matrix that we've written down here represents the original system of equations. And what we're going to do next is work with the matrix. It's much easier to work with computationally than it is to work with the system of equations. So we're going to take this matrix that we got on the last slide, and we're going to put it into what's called reduced row echelon form. So the RREF that you see here, what that stands for is reduced row echelon form. And to do that, we're going to go to our calculator. Don't worry too much about doing this by hand. If you need that, you'll get it in a later class. But what we're going to do is enter this matrix into our calculator. So if you get out your TI-83 or TI-84, first thing that I'm going to go into is the matrix menu. So if you hit the second button and then this X inverse button, you'll notice that it says matrix right above that. So you should see something that looks like the following. I'm going to scroll over to the edit menu and select my matrix, say A. It doesn't really matter where you put it. Now, the first thing that I have to enter is what's called the dimensions of this matrix. The first number is going to be a 3. That stands for 3 rows in our original matrix. And if you look back at this matrix, rows are always horizontal and columns are always vertical. So in this matrix, we have 1, 2, 3 rows, 1 row corresponding to each linear equation in our original system. In a similar way, we have 4 columns. 1, 2, 3, 4 columns. 3 of those columns represent the variables that we originally had present, an x, a y, and a z. And the 4th column represents the right-hand side, the constants that appeared after the equality. So my matrix in this case, A, is going to be a 3 by 4 matrix, 3 rows by 4 columns. Now if I hit enter, what my calculator is going to do is give me a place to put all of these numbers. So I'm just going to start entering these numbers in one at a time. In my first row, I get 1, -2, 3, and then 11. You'll notice here that the calculator doesn't put in that vertical line. There's no way to put that in with the TI-83s and the TI-84s, but again, mathematically, it's not going to make any difference at all. In my second row, I have 4, 2, -3, and then after the augment, which is not in my calculator, another 4. Third row is 3, 3, -1, and 4. Now, what I have here is a 3x4 matrix. All of my numbers are appropriately entered. What I want to do next is hit second and quit. And this is an important step. What that's going to do is take me back to the home screen where you would do your normal computation. Next up, I'm going to go back into the matrix menu. This time, I'm going to select the math submenu here. So I'm going to use my arrow key to scroll over 1, and then I'm going to scroll down until I see RREF, that is reduced row echelon form. And in my calculator, it's the 12th entry down, maybe a little bit different in your calculator. So I'm going to select reduced row echelon form. That's going to put that RREF on my home screen. And then I'm going to go back once again into my matrix menu. And I'm going to select the matrix A. Close up the parentheses, hit enter, and what it's going to give me is the reduced row echelon form of the original matrix that represented the system that I'm interested in. So, given that, let's go back to the blackboard here and see how that solves our system. So, we've now used our calculator to compute the reduced row echelon form of the original matrix that we were interested in. And what we came up with, according to our calculator, was the following matrix. This is in reduced row echelon form. So you'll notice here that I've put the augment in by myself, but the 3, -1, and 2, I'm just reading straight off of my calculator. Now, what we're going to do is take this matrix and translate it back into its corresponding system of equations. And when we do that, we get the corresponding system. X equals 3, y equals -1, and z equals 2. So you'll notice here that this first equation in my system is coming from that first row. So this red row up here corresponds to this red equation down here. Next up, the second row in my matrix corresponds to the second equation. And finally, the third row in my matrix, which I've outlined in blue here, corresponds to the third equation in my equivalent system. Now, what this does is gives me a solution to the original system of equations that I was interested in, which, if you look back on the last slide or at the beginning of this video, was x minus 2y plus 3z equals 11, and so on down the line. So what this says is that if I was to plug in x equals 3, y equals -1, and z equals 2 into this system, I would get 3 true statements. Now this is very convenient. Don't worry too much about the details of what your calculator is doing here. As long as you can do the computation with your calculator, it's sufficient for this class. The really big upshot of this is it saves you a lot of computational time doing elimination or substitution. What your calculator is actually doing here is the elimination method, but it doesn't really matter too much. This is a very quick way of using your calculator to solve systems of linear equations. So let's put that to work for us in the following word problem. So in this exercise, a diabetic patient wishes to prepare a meal consisting of roasted chicken breast, mashed potatoes, and peas. A 3-ounce serving of roasted skinless chicken breast contains 140 calories, 27 grams of protein, and 64 milligrams of sodium. A 1-cup serving of mashed potatoes contains 160 calories, 4 grams of protein, and 636 milligrams of sodium. And finally, a 1-cup serving of peas contains 125 calories, 8 grams of protein, and 130 milligrams of sodium. So we want to know how many servings of each should be used if the meal is to contain 415 calories, 58.5 grams of protein, and 553 milligrams of sodium. So Our job is to figure out how much chicken, how much potatoes, and how much peas we should be putting into this meal. And just like every other word problem, the first step that we need to take is to define our variables. In this case, I'm going to let X be the number of servings of chicken, Y be the number of servings of mashed potatoes, and Z be the number of servings of peas. Our next step is to define our equation, but in this case we're not actually going to get one equation. We're going to get a system of 3 equations in 3 unknowns, one for the X, one for the Y, and one for the Z. So, looking back at this problem, you'll notice that I have a bunch of information about calories. So my chicken breast contains 140 calories per serving, mashed potatoes 160 per serving, and finally my peas contain 125 calories per serving. So I'm going to write down my calorie equation as follows. 140 times the number of servings of chicken plus 160 times the number of servings of mashed potatoes plus 125 times the number of servings of peas is going to give me a total desired number of calories as 415 calories. So what I have written down so far is my calories equation. And if you look back in the statement of the problem, I'm going to have another equation for protein and finally a third equation for milligrams of sodium. So what we have here is a system of 3 equations in 3 unknowns. Now we're going to take that, and in order to solve this system of 3 equations and 3 unknowns, enter this into your calculator using the associated matrix. Use that to get the reduced row echelon form, and what you'll see is the solution of this system is x equals 1.5, y equals 1/2 or 0.5, and z equals 1. So finally we're going to state our answer in terms of a sentence with units. So what we just found out is that our meal should contain 1.5 servings of chicken, 1/2 servings of potatoes, and 1 serving of peas. So with that said, you should have enough information to complete the SLO on matrices.